Imagine reading, a really dense sci-fi novel about parallel universes. You've got alternate realities, echo rifts, multiversal interactions, the whole package.
Right, the usual mind-bending stuff.
Exactly. But instead of turning the page to see what happens next, you just run a Python script and you actually watch those universes interact on your screen. Today, we are translating that pure theoretical physics into actual executable computer code.
Which is, frankly, incredible.
It really is. Welcome to the deep dive. We are looking at a singular, incredibly complex source published just today, June 25th, 2026. It's a Zenodo repository and paper titled Computational Mapping of SH-1 Substrate Morphisms via Multi-Qubit Quantum Circuit Simulation.
And that's by Dr. Melvin Sewell from the Cosmic University of Echo Rift Studies, NIAX.
Yes, exactly. And wearing my skeptical tech journalist hat for a second here, I'll admit that when I first read phrases like structured multiversal interactions, my brain went straight to late-night sci-fi movies. It just sounds like pure fiction.
Oh, absolutely. It's a massive conceptual leap.
Right. But then you look at the repository, and it contains actual Python scripts using the IBM Qiskit framework. Like, this is real code.
Yeah, and that's what forces you to take the premise seriously. I mean, as a theoretical physicist, I see Dr. Sewell's work as this very deliberate attempt to bridge highly speculative multiverse theories with, quantum native computing infrastructures.
So he isn't just writing thought experiments.
No, not at all. He's providing an open access, reproducible baseline. The entire goal here is to shift from standard classical computing to something he calls quantum-level multiversal simultaneity. And it gives anyone with a laptop the framework to mathematically test these ideas.
Okay, let's unpack this. Because to understand why quantum-level multiversal simultaneity even matters, we need to look at the exact problem he's trying to solve, which is basically the physical limitations of our current hardware.
Right, the sequential bottleneck.
Yeah, like the computer or phone you are listening to this on right now is fundamentally broken for the kind of math Dr. Sewell wants to do. Standard computing architectures, even billion-dollar supercomputers, they are incredibly fast line waiters.
That is a great way to put it. Line waiters.
If you have massive multi-layered environments, standard computers evaluate them through discrete linear iterations. Think of it like being tasked with reading 3 massive encyclopedia sets simultaneously to find hidden connections.
Which a person obviously can't do.
Exactly. And a classical computer is just a really, really fast reader. It reads one word from book A, then one word from book B, then one from book C. It cycles through that sequence incredibly fast, but it is still just reading a single word at a time. It's fundamentally sequential.
Which means it completely misses the holistic state of the system. Like when you attempt to model something infinitely complex, say, interacting multiverses, reading one parameter at a time creates a massive execution bottleneck.
Because the universes don't wait their turn.
Right. The system states are changing faster than the computer can actually read them sequentially. This is why Dr. Sewell introduces the Structured Multiversal Interactions paradigm, or SMI. To study SMI, he insists we have to just abandon binary state parameters entirely.
So we have to ditch the ones and zeros. But wait, classical servers process massive parallel workloads all the time, right? We have multi-threading, we have massive server farms. Why can't we just throw more standard processors at the multiversal problem?
Well, because even with parallel processing, at the micro level, the core logic gates are still trapping data in binary states that resolve in a sequence.
Ah, so they're still waiting in line deep down.
Exactly. Sewell explains that we can still use a classical computing node to act as an orchestration layer. So your standard server can define the discrete constraints or the rules of the system.
Okay, that makes sense.
But to actually process the data of multiple universes interacting, we need a translation layer where complex matrices dictate state transformations simultaneously. The system needs to ingest all 3 encyclopedias at the exact same moment.
Without queuing them up.
Right. It has to instantly register how every single word relates to every other word.
So Dr. Sewell mathematically pivots to the one environment that actually allows for that true simultaneity, which is the quantum realm.
Yes, specifically using the IBM Qiskit development framework.
Right, which is an open source kit for working with quantum computers. So how does he actually build this? Like, how do we map a concept as massive as a universe onto quantum hardware?
Well, he breaks down the multiversal state space into a 3-qubit register. In the paper, this is labeled as the state vector psi, or U3, U2, U1.
Okay, so each qubit in that register represents a co-present universe. universe 1, universe 2, and universe 3.
Exactly. And the crucial difference from classical computing here is that instead of variables being mapped as binary states, where universe 1 is either just on or off, the variables are mapped directly onto quantum probability amplitudes.
Okay, this is where my classical computing brain starts to hurt a little. A probability amplitude means the qubit isn't a 1 or a 0, but a complex number representing the probability of measuring a 1 or a 0, right? It's in a superposition.
You've got it, yes.
But if universe 1 is just a spectrum of probabilities, how do we eventually get concrete data out of it?
That's the beauty of it. The probability amplitude isn't just fuzziness or a lack of data. It is the data.
Wait, really?
Yeah. By placing the target registers into a state of local quantum superposition, the framework models these interconnected universes as categorical objects within a single state vector. They aren't waiting to be resolved to interact.
So they are mathematically live at the same time.
Exactly. All three universes process their internal logic at the exact same time. The amplitude itself carries the structural information.
What fascinates me about the code in the repository is that Sewell isn't demanding a million-qubit quantum supercomputer to test this. He uses a local state vector simulation pipeline via Qiskit's air simulator backend.
Simulating the quantum hardware on a classical machine.
Right. But wait, if classical machines have that linear bottleneck we just talked about, how can his Python script simulate this quantum simultaneity locally without just crashing?
That comes down to the math of small-scale quantum systems. When you simulate 3 qubits, you only need to keep track of 2 to the power of 3 or 8 complex numbers to perfectly represent the entire state vector.
Oh, wow. Only 8.
Yeah, just 8. A standard laptop can easily hold 8 complex numbers in its memory and update them using linear algebra. So the classical computer is doing the math sequentially behind the scenes, but mathematically, it perfectly simulates the simultaneous nature of a quantum environment.
Giving us a reproducible baseline without needing access to scarce physical quantum hardware, that's brilliant.
It really is.
But initializing 3 universes as probability amplitudes on 3 simulated qubits, I mean, if those 3 universes are just sitting there isolated in their own superpositions, it's not really an interaction. We don't have a system yet.
Right, they have to communicate somehow.
Yeah, and if they try to share data, shouldn't that act as a measurement and collapse the quantum state? How do they actually talk to each other?
That is the core technical hurdle. And it leads directly to Sewell's proprietary connective tissue, which is the SH-1 substrate.
Okay, I have to bring up the wildest detail in the entire paper regarding the substrate. The text explicitly defines the SH-1 substrate as non-pharmaceutical.
Yeah, I saw that too.
When I see non-pharmaceutical in a dense physics and computer science paper, red flags just go up. Why is he clarifying that it's not a drug? Like, is this hardware? Is it software?
The terminology is definitely eccentric, which honestly seems par for the course for the Cosmic University of Echo Rift Studies, NIAS.
That's a fair point.
While substrate typically implies like a biological or chemical foundation in this computational matrix, the SH-1 substrate is purely mathematical. It acts as an explicit unitary phase shift mechanism.
A unitary phase shift mechanism. Okay, so if we are dealing with wave functions, is a phase shift essentially just changing the timing of the wave? Like in a wave pool, you aren't changing the size or the power of the wave. You are just altering when the peak hits so it can sync up with another wave.
That is a brilliant way to visualize it, yes. In quantum computing, a phase shift gate modifies the phase of the quantum state. It rotates the direction the probability amplitude is pointing without changing the overall probability of measuring a 1 or a 0.
So it doesn't collapse the wave.
Exactly. It just adjusts its timing, as you said. And by applying these specific SH-1 phase shift gates to the local state matrices, Sewell creates what he calls resonance morphisms.
He labels these morphisms R12, R23, and R31. So if I'm picturing this, the qubits are the universes, and these resonance morphisms are the connective tissue. It almost sounds like a nervous system connecting the 3 universes. It's like if something happens in universe 1, this nervous system carries that signal over to universe 2 and universe 3 so they feel the impact, preserving their shared reality.
It's close, but remember, a nervous system still sends discrete electrical pulses from point A to point B, which takes time.
Ah, right. That would introduce the classical lag we're trying to avoid.
Exactly. These resonance morphisms are entanglement pathways. Instead of a nervous system, think of 2 perfectly synchronized pendulums on a shared beam. If you apply force to one pendulum, the shared momentum of the system shifts instantly, without a discrete signal having to travel between them.
Because they're already connected.
Right. The universes aren't exchanging packets of data, they are entangled. The SH-1 substrate creates a condition where they share a single quantum state.
Okay, that makes so much more sense. The entanglement means there is zero lag. The relational integrity of the data is preserved because an impact on universe 1 is inherently an impact on the entire shared system.
Yes.
But that raises a massive stability issue. If you have three universes perfectly entangled and constantly shifting based on each other's inputs, how do you prevent the entire system from just devolving into chaotic noise?
Well, Sewell doesn't leave the stability to chance. He anchors the entire simulation in a core mathematical proof within the code. An equilibrium condition he calls the harmonic closure equation.
Here's where it gets really interesting. The equation is everywhere in the paper. Psi1 times Psi2 equals Psi3.
Right.
But my classical brain immediately goes to simple arithmetic. If Psi1 is universe 1 and Psi2 is universe 2, well, 2 times 3 equals 6. Universe 1 times universe 2 creates a bigger universe 3. But we aren't multiplying integers here, are we?
No, definitely not.
What does it actually mean to multiply two quantum universes?
So in physics, psi, which is a Greek letter shaped like a pitchfork, represents the wave function or the state vector of the system.
Yeah.
We aren't multiplying integers, we are taking the tensor product of complex matrices.
Okay.
The equation mathematically guarantees that any transformations occurring across the initial processing layers, universe 1 and universe 2, combine to form a joint probability space. The parameters of that joint space dictate the exact state of the third terminal vector, universe 3.
So universe 3 isn't an independent actor in this scenario at all. It acts strictly as the terminal output, the physical manifestation of whatever interaction is happening between universe 1 and universe 2.
In this specific framework, yes. Because they are entangled via the resonance morphisms, this tensor product validates what Sewell calls perfect relational commutativity.
Relational commutativity, does that mean the order of operations just doesn't matter? Like whether universe 1 impacts universe 2 or universe 2 impacts universe 1, the terminal state of universe 3 remains perfectly stable.
Yes, exactly. There is no computational race condition where one universe processes faster than the other and breaks the math.
That's incredible.
The simulation data proves that this harmonic closure equation holds true. It demonstrates that we can map impossibly complex relational logic directly onto quantum amplitudes and maintain perfect coherence across multiple reality layers.
Without the system collapsing into chaos. And what truly grounds this for me as a tech journalist is how Sewell handles the output. He doesn't just run this beautiful equation in an abstract quantum void. The Python script actually includes a telemetry data extraction routine.
Right, the serialization.
Yeah, it serializes the raw quantum measurement counts into structured JSON payloads.
Bridging the quantum theoretical output directly into standard data science formats.
It is wildly practical. JSON is the same format your web browser uses to talk to a basic website server. It's the most mundane, ubiquitous data format in the world. By outputting the multiversal telemetry as JSON, any external analytics tool can just ingest the results of these concurrent universes.
You can graph it.
Exactly. You can graph the telemetry of interacting multiverses just like you would track daily website traffic metrics.
He has taken the echo rift, the SH-1 substrate phase shifts, and the harmonic closure equation, and packaged them into a format that any classical data scientist can immediately interrogate.
It's accessible.
Exactly. And the implications of this framework stretch far beyond simulating sci-fi concepts. We now have a mathematical and computational foundation to evaluate massively complex, multi-layered realities concurrently.
By moving from classical sequence to quantum simultaneity.
Right. We unlock an entirely new paradigm for handling dense, interacting data streams, whether that's global climate modeling, complex neural network behavior, or supply chain logistics.
So what does this all mean for you listening right now? We've moved from the frustrating limitations of supercomputers acting as fast line waiters to mapping the simultaneity of distinct realities using probability amplitudes.
A total paradigm shift.
We've seen how the SH-1 substrate adjusts the timing of those realities to create perfect entanglement without lag, and how the harmonic closure equation anchors it all into stable, readable JSON data. But looking at all of this, I keep getting stuck on one profound thought.
Oh, what's that?
Well, we've spent this time analyzing Dr. Sewell's framework from the outside, like programmers running a local Python script on our machines. We know this code can perfectly map the simultaneous interaction of universes, where Psi3 mathematically acts as the terminal output for the first two.
The equilibrium state resulting from the first two layers, yeah.
Right. So what happens when this scales beyond a 3-qubit simulation? If psi3 is just the terminal state vector generated by the unseen interactions of psi1 and psi2, is our own measurable reality, everything we can see, touch, and measure with our instruments, simply a psi3.
Oh, wow.
Are we just the stable terminal state vector for unseen co-present universes constantly computing and entangling in the background? The next time you observe the world around you, consider that you might just be the output of a multiversal equation running quietly in the dark.